Okay, welcome to the second part of my week 5 videos. In this part, I will be going over our quiz from this week. Alright, so let's see how you did. Just to recap, let me read the problem. Two blocks with masses m1 and m2 slide down an inclined plane at angle theta. There is friction between block 1 and the plane with coefficient mu, but none between block 2 and the plane or between the blocks. Okay, in part A, you were to draw the free body diagrams for each block and for the system of both blocks without assuming Newton's third law. Okay, so we also have to assume that the blocks move together. Okay, so here's part A. Let's look at the picture for block 1. Here is our first free body diagram over here. And for block 1, we have we have one surface in contact with block 1 from below and another from the side. So we have two surfaces of contact. However, there is only friction between the ramp and the block and not between the two blocks. So from the ramp, we have two components of the force of contact. We have the component which is perpendicular to the ramp, N1, and the component which is parallel to the ramp, slowing down the relative motion between block 1 and the ramp. And this is the kinetic friction force, which we know takes on a constant value of mu N1, not mu N2. So now that I fixed that, we have yet another surface in contact with ramp 1, with block 1 rather, okay, and it has a component perpendicular to the surface, the interface between block 1 and 2, and we do not know its magnitude, so we'll call it F21 for force of block 2 onto block 1. Now recall there's no friction between the two blocks, so there is no component parallel to this interface between block 1 and block 2. Okay, so that's our third force, and lastly, there's the influence of gravity, which points straight down towards the ground, and a magnitude of m1g. Okay, block 2. So, we have the same surface in contact with block 2 as block 1, which would be the ramp, and now we have block 1 also in contact with block 2. So from the ramp, we have the normal force N2, right? But there is no friction on block 2, so we have no force component parallel to the ramp. Now from block 1, we have the force F12, okay? This is the force perpendicular to the interface between block 1 and 2. And because there's no friction between the blocks, there is no force parallel to the interface between blocks 1 and 2. Okay. Lastly, there's the influence of gravity, which has a force m2g. Lastly, it asks us to draw the free body diagram for the system of blocks. So, we're viewing these two blocks here, as just one large mass, with a total mass of m1 plus m2, right? So there's no interface between blocks 1 and 2 anymore, it's just one homogeneous mass. Okay? In this situation, we have a total normal force coming from the ramp. Okay? And now the friction force, though, is still just the friction force on block 1, or due to block 1. So on this whole body, it will be that friction force mu n1. Okay? Lastly, there's the influence of gravity on this total system, and the total system has a total mass of m1 plus m2, so our gravitational force is m1 plus m2g. Now, part B. Before we go to part B, it said not to assume Newton's third law. So we are not assuming Newton's third law by saying this force F21 and F12 have two different labels, so we have not said that their magnitudes are equal, right? Newton's third law says that the forces, right, between two surfaces, so the force that one surface exerts on the other, has to be equal to the reaction force. Okay, so if I push on the table, the amount of force that I exert onto the table is exerted back on me. Okay, so in general, forces come in pairs, and this is true everywhere. For example, you are feeling a gravitational force due to the Earth. Well, did you know that the Earth also feels a gravitational force due to you? Okay, so even that gravitational force comes in pairs. However, we're not usually interested with your influence on the Earth, so we don't draw a free body diagram on the Earth, but if we did, right, we'd have to include the force that you exert on the Earth. Okay. So, part B. Part B says to find the acceleration of the system. Okay, this is most easily done if we do not have to deal with these pesky contact forces F21 and F12. So let's look at the entire system here. Alright? So we're only dealing with the unknowns, fewer unknowns in this situation. So let's deal with the total system of masses 1 and 2 together. Okay? And we'll just have 3 forces to deal with. So if we sum the forces, well, before we do that, let's pick a coordinate system. So the most convenient coordinate system is one where we have the positive x direction in the direction of acceleration down the ramp, and the positive y perpendicular to the ramp pointing straight out. Okay? So now let's just write each force in component form for this coordinate system. So looking at this free body diagram, the normal force is all in the y direction, so normal force is 0I plus nj. F, friction force, is all in the negative x direction, so we get negative mu1 n1I plus 0j, 0j because there's no y component. And lastly, there's gravity, which points straight down, which is not either in the xy, positive x, positive y, or negative x, negative y direction. Okay? So it's somewhere between these directions. And some of you are still confused about how to write a vector like this, which is in between two axes, okay, in component form. So I drew a quick sketch for you. The first thing you do is draw this coordinate axis, the y-axis, both positive and negative, and the x-axis, both positive and negative, okay? Then you draw the vector mg straight down, which I've indicated in blue. Next, we draw any given angles, okay? And the one angle we are given in this problem is the angle between the horizontal, the ground, and the incline, theta. So, we've defined these axes, so the x-axis is up at an angle of theta, okay? So, from the horizontal, which is this red line, we know that to the negative x-axis, or just to the x-axis in general, there's an angle theta. Okay. Now we just use the rule that the sum of angles which are extended through two perpendicular lines is equal to 90 degrees. Alright? So the first set of perpendicular lines, that I'll use is the negative x-axis and the negative y-axis. The sum of the angles that extend through this line must be 90 degrees. So this angle here, theta, plus this angle between the red line and the black line is equal to 90 degrees. Okay? So this angle here is 90 minus theta. Now let's look at two other perpendicular lines, which is this red line and this blue line. So the sum of this angle, 90 minus theta, and the angle from the blue line to this little orange, or black line I have here, is equal to 90 degrees, and I've already drawn in that angle is theta. Right? Okay, now I make myself a triangle. We have a line down the y-axis and a line parallel to the x-axis, which makes the triangle a right triangle. We know this angle is theta. We know the hypotenuse has a length of mg, so using trigonometry, we know the x component, or the component which is parallel to the x-axis, is equal to m1 plus m2g sine theta. So notice here that little m here, is equal to m1 plus m2. Alright, and that's positive because it's pointing in the positive x direction, And the y component is minus mg cosine theta, right? Minus because this mg vector points in the negative y direction, okay? All right, so now we have all the forces and components on the system. We go ahead and sum all the x components together, right? So 0 plus minus mu1 n1 plus m1 plus m2g sine theta is equal to ma. And here that is. That's equal to ma. All right, where m is m1 plus m2. A will be the total acceleration, standing for the acceleration down the ramp. That'll be the total acceleration of the body if this body moves together, which in this case it should, or it is. Okay? So we could go ahead and solve this equation for A here. Solve equation for A. But, right, we don't know this unknown n1 here. So to get n1, we look, well, is there another free body diagram that contains n1? Yes, this first one, right, from just block 1. N1 is in the y direction. So if we sum the forces in the y direction on block 1, what will we get? We'll get N1 minus, and then for similar reasons as this other vector decomposition here, we'll get the y component of M1g to be M1g cosine theta with a minus sign in front. So we get N1 here minus M1g cosine theta is 0, which tells us that N1 is M1g cosine theta. Now we plug that in here, this result for N1, okay, and we solve for A by dividing both sides by M1 plus M2, the coefficient in front of A, and we get this result, where I just have M1g cosine theta in place of N1. So that is the acceleration of the system, most easily found by using two free body diagrams, the free body diagram of the combined system, and then in this case, since we had friction just on block 1, we had to go ahead and use the free body diagram for block 1 just to find what N1 was, okay? We did that. What was the law or definition we applied here? Well, that wasn't straightforward. It was this sum of the forces equals ma. Now for problem C, okay, it says to show that Newton's third law is valid. Okay, so what is Newton's third law in this problem? Well, it's a bit vague, but it's talking about to show that Newton's third law for the interaction between block 1 and 2 is valid. Okay, and for the interaction between block 1 and 2, Newton's third law says that the force that block 1 exerts on block 2 must be equal to the force that block 2 exerts on block 1. Okay? So let's go ahead now, and if we sum the forces on block 1, so we go back to block 1's free body diagram, we sum the forces in the x direction, we will get F1 minus mu m1g cosine theta plus m1g sine theta is equal to m1a, right? So you might do this, and you might say, okay, I got mu n1 here, right? Now remember, we solved for n1, found it to be m1g cosine theta, so I'm just making that substitution right away. Okay, so let's go ahead. The strategy here is to prove this relationship. Okay, so we'll solve for m1, plugging in the acceleration we found. We'll solve for m2, plugging in the acceleration we found in part B. Okay, and then we will see if the two expressions are the same. All right, so from the sum of the forces in the x direction on mass 1, we have this expression here which we can solve for F1. All right, now I'll do that by adding these two terms to both sides. And for A, I'll plug in my result for B. So this whole thing in brackets here is my result from B. And now we'll go ahead and simplify this expression up here. Okay, let's look at this first term here, right? I can go ahead and split the sum in this numerator. I can split it up. So I divide each term by the denominator, and the denominator is m1 plus m2. So for this term here, m1 plus m2 will get canceled, and we'll multiply it by this m1 way out in front of these brackets. What's left will be m1 times g times sine theta. Okay, that'll be left for this term. Now notice that that term appears exactly over here with a minus sign. So those two terms will add together to give you 0. So I've crossed them out in red. Okay, now this next term here is going to be minus mu m1g cosine theta, right, times m1. Okay, so let's go ahead and in this next step, let's go ahead and factor out. All right, so I think there's a mistake. No, that's right so far. Except this here should say, oh no, that's fine. This is all right. Okay, good. Okay, so notice that each of these terms have the common factors of mu m1g cosine theta. So what I have left is if I factor those two terms out, all right, mu m1g cosine theta, I factor out that common factor from this term and this term, I'll be left with 1 here, right? So we have 1, and then minus, so this minus sign, and then after I factor this common term, I'll just be left with this m1, which is multiplied, right, throughout both of these terms, okay? So I have two terms left. The 1, which comes from this term, minus, which comes from this minus sign, m1 here, divided by m1 plus m2, right? And I factored out this common mu m1g cosine theta here and here from both of these terms, okay? Now I can simplify by adding these two numbers together, 1 and m1 over m1 plus m2. So I do that by finding a common denominator, which is m1 plus m2. I write 1 as m1 plus m2 divided by m1 plus m2, okay? And when I do that, I see that these m1s will cancel up here in the numerators, and I'll be left with m2 divided by m1 plus m2. So factoring out all the mass terms, just putting them over to the right side, I get mu mg cosine theta, right, times this m1 here, right, times the m2 that's left over, and then divided by m1 plus m2. I found that for F1. Now to prove Newton's third law, I'm going to solve for F2 and show that that's the same as F1. So if I look at block body 2, and I sum the forces on the x direction, right? So let's go back to free body diagram of body 2 since it's been a while. Here it is. We sum the forces in the x direction, we'll get m2g sine theta minus f12. All right? Or I just call this f2, or did I call it f1? What did I call it down here? I called it, I think, just f2. All right, yeah, f2 instead of f12. Okay. So let's go ahead and solve for that. Here, we're going to solve for f2. So I add, or rather, I go ahead and switch the places of m2a and f2 in these equations. All right, and I'll get f2 is equal to m2g sine theta minus m2a. Right. So you can do that. That's just achieved by adding f2 to both sides and then subtracting both sides with m2a. Alright. So now I plug in that a I got from part B, which I've now written in these brackets. Okay. And then in a similar fashion, right, this term will cancel this term. In a similar fashion to what happened with f1. Alright. So in the end, we will find that f2, we do this algebra here, which is simpler than last time, okay? We'll get that is equal to mu g cosine theta m1 times m2 all over m1 plus m2, which is the same as f1. So we've shown that these two forces are equal in magnitude. All right, so just to fix this up, in my calculations below, I called this force here f1 and the other force f2. Okay, so let's make that correction. So these are the free body diagrams we used in part C. Alright, here they are. Okay, hope you enjoyed these videos. I hope they were helpful. Have an A1 day.